Assalamu alaikum dear students. Hi, how are you? Hope you are doing well. Today we are going to study de Broglie wavelength. Louis de Broglie was a scientist who derived an equation which shows the wave characteristic of the electron. First of all, you must have to know what's a wave. I think to understand this lesson, you should have a little bit information about the wave and frequency and this all kind of stuff. Okay, so you can observe a wave over here. So from this part to this part, this distance is known as wavelength, or otherwise we can also say this to distance also known as wavelength. So this is the wavelength. Let's carry on our lesson. Louis de Broglie in 1923, a French physicist, he proposed the hypothesis to explain the theory of atomic structure. He says that small particles like electron, they show wave-like properties. Okay, his hypothesis was proved correct with some other scientists' experiments, and that's why he got Nobel Prize in 1929. Let's have a look who performed experiment on his hypothesis. There was two scientists, Clinton J. Davison and Lester H. Germer. They say that if we shot an electron onto a nickel crystal, it behaves like a wave of the X-ray, like the diffraction against the crystal. That's why they say that they approved the saying of Louis de Broglie that electron has a characteristic of a wave. Electron could be a particle and also a wave because its motion is a wave motion around the nucleus. Let me tell you again simply, when X-ray was shot on the nickel crystal, it shows some diffraction. Diffraction is a kind of characteristic of the wave. And when they shot electron to the nickel crystal, it again show same kind of property like a wave. So they approved with the experiment that the hypothesis of Louis de Broglie was true. So they performed experiment in 1929, and after 2 years they performed experiment in 1927, and after 2 years in 1929, Louis de Broglie earned Nobel Prize. So the Louis de Broglie was true. Let's have a look at the diagram. Students, over here you can see this dot circle is the path of the electron. Okay, so when electron is moving in a circular motion around the nucleus, is not moving in a straight circular path. It moves like a wave. So how can we find the wavelength of the electron that is moving with a different speed in different velocities? That's the thing that Louis de Broglie wanted to explain us. Let's have a look at the Louis de Broglie's wavelength equation. How did he derive the equation? Let's derive or find out the de Broglie wavelength equation. How de Broglie first found this equation? Actually, he used the Einstein's famous equation relating matter and energy. We know that Einstein said E is equal to mc square. Over here, E is energy, m is for the mass, and c is the speed of light. E is energy, m mass, and c is the speed of light. This is the equation, famous matter and energy relating equation of Einstein. And Max Planck has said that E is equal to h times nu. This equation says every quantum of a wave has a discrete amount of energy. It's known as Planck's equation. Over here, E is energy, h is Planck's constant, and nu is frequency. It is not v, it is not velocity, it is nu, it's known as frequency. So, as we have seen that these both are equal to the E with the energy, so we can write it something like this. We can write, instead of E is equal to mc square and E is equal to h times nu, we can write mc square is equal to h times nu. Nu is the frequency. From the waves, we know that frequency is equal to velocity by wavelength. Velocity by wavelength, or the speed by wavelength. For a photon, we can write it like this. Nu is equal to c by wavelength. For example, we know that what's the unit of frequency? It is 1 by second, or we can also say hertz. What's the unit of speed or velocity is meter by second. What's the unit of lambda? It's meter. If we cancel meter by meter, again, what's remaining? 1 by second, which means that it's 2. So frequency is equal to c by lambda. If we are using it for a photon, for sunlight, we use c. If we use it for ordinary particle, not photon, we can use v. Both of them are correct. So right now I have substituted the actually de Broglie substituted the the frequency with c by lambda. Over here we can see that mc square is equal to h times c by lambda. We can cancel this c with the square. What's the remaining? The remaining is mc is equal to h by lambda. So according to de Broglie, every particle has a wave characteristic. So we have to find out the wavelength of a particle. So we can multiply lambda at both sides. We can cancel lambda by lambda, and we can divide mc at the both sides. We can cancel mc and mc. So what's remaining? Lambda is equal to h by mc. Lambda is equal to h by mc. You can see over here. And the students, if this equation is for the photon of light, which has a very high velocity, very high speed, and if we want to use it for an ordinary particle, some other thing like than photon, like an electron, so we can use v instead of c, because they both show the velocity. So if we want to use it for a photon, is a constant, so we can use this equation. But if we want to use it for another particle like electron or something else, we can use this equation. So this is the de Broglie wavelength equation. In this place, lambda is wavelength, h is Planck's constant. It has a value of 6.626 times 10 to the power of minus 34 joule times second, and m is the mass and v is the velocity. Okay, students, let's work an example from this equation. Over here we have question. It says that find the de Broglie wavelength of an electron moving at a speed of 5.0 times 10 to the power of 6 meter by second. So let's solve the question. Is the equation as we have derived a few seconds ago. So what's the question? We have to find the de Broglie wavelength, which means that lambda is equal to question mark of an electron. What's the mass of an electron? Mass of an electron is 9.11 times 10 to the power of minus 31 kilogram. Moving at a speed of, this is the speed of electron moving. We know that this is a constant, so value is given. You have to remember the Planck's constant value, and you have to remember the mass of an electron we have studied in the previous lesson. So let's find out what's the wavelength of the electron that is moving at a speed of 5.0 times 10 to the power of 6 meter by second. Actually, it's something like this. We have a nucleus, and an electron is moving in this orbit in a shape of wave. So we have to find the wavelength of this electron, lambda. So if you put the values, we have put the value of Planck's constant is 6.626 times 10 to the power of minus 34 joule times second, and now we have put the value of m, the mass of electron is 9.11 times 10 to the power of minus 31 kilogram, and we have put the speed of electron, the velocity 5.0 times 10 to the power of 6 meter by second. We know that joule is made up of Newton times meter, and Newton times meter is kilogram times meter square by second square. So, and over here we have multiplied these two, 9.11 times 5.0, it makes 45.55, and we took 10 as a base, and minus 31 plus 6 kilogram times meter by second. We can cancel this kilogram by this kilogram, meter by its square, and these 2 seconds with these 2 seconds, what's remaining? Only meter. So we again simplify this. Now it will take a shape of 6.626 divided by 45.55 times 10 to the power of minus 34 divided by 10 to the power of minus 25 meter. Minus 31 plus 6 makes minus 25. So if you divide this with 45.55, it will become 0.145 times, and minus 34. If we know that if we take it to the nominator, is symbol will change, and it will become plus 25, and 10 to the power of minus 34 plus 25 makes 10 to the power of minus 9 meters. So it's 0.145 times 10 to the power of minus 9 meters. We can simplify it again. We can write it 1.45 times 10 to the power of minus 10 meters. We know that 10 to the power of minus 10 meter is angstrom, so we can write it like this: 1.45 angstrom. This is the wavelength of electron that is moving with the speed of what was the speed? With the speed of 5.0 times 10 to the power of 6 meter by second around the nucleus. Okay, students, thanks for watching today's video. Hope you will study well, and if you have any questions and suggestions, write in the comment section below. Take care of yourself. Goodbye.